Jörgen.
Jörgen Brandt, and he's talking about modeling Erlang purposes as Petri.
For the introduction. So my name is Jörgen, and I'm studying in Berlin at the Humboldt University, and I'm currently finishing my PhD. And today I'm going to talk about Petri nets and how to use them in Erlang. And before I begin, I want to say a few words about software engineering. So since Petri nets are a technique for modeling software, I think I need to clarify that. So usually when we're modeling software, when we're drawing a model on a piece of paper, and then throwing away the paper and open the laptop and start hacking C code, then that's probably a bad idea, right? So, the realm in which we see software engineering is that there's the model and then there's the code, and these are two separate things, but this really shouldn't be the case. I think that software models should be dragged into the realm of the executable and into the realm of the testable, and that is very important. And this is also what I've tried to do for Petri nets, and what I'm going to talk about today. So first of all, what makes Petri nets so suitable for modeling distributed software is they're not only understandable in code, so I will show you how to code such models, but also there's a visual expression of the model, and this is something very intuitively understandable. It certainly needs a little bit of practice to read these models, but only to have a representation that fits on a slide and that you can look at and that is immediately understandable is a great help, as opposed to only having the source code to look at. And the second thing I really like about Petri nets is that since there is a defined semantics, we can look for properties that are important to us, like if they terminate or if they're alive, or we can look at invariants, for example, that something that is in the system can be passed around but can never disappear. That would be an invariant. And we can make up a notion of correctness and check it formally. And the third thing that is very good is that since they're complete descriptions of a program, we can execute them, we can test them, we can iterate on them. It doesn't need to live in the realm of the document. We want to drive software from it. So first, let me introduce you a little bit to the terminology. So in a Petri net, we have passive things and active things, and the passive things we call places, and these are the circles here. And a place, a passive thing, is like a box or a storage or a buffer, something static that can hold something. And these are the circles. Here we have the place with the name down that's holding a monitor reference, so that it can be data on them. And the active things are the boxes, which we call transitions. And a transition takes something from its preset places, which are here down and busy, and produces something on its post-set places, which is here idle. And the third thing that is important about the kinds of Petri nets I'm talking about is that they exist in an environment, so that they're not just self-contained systems, but they need to communicate to the outside. And that's why they have to have an interface. And here the places that are on the interface are essentially the interface over which the Petri net can take data from the outside and send data around. And we will see that these Petri nets will end up as Erlang processes. So we can make these processes receive and send messages just like any other process in Erlang. And what is also important to note is that not only the data that can appear on places can be any Erlang data structure, but also the things that the transitions do can be any Erlang function. So the transitions are in themselves like Turing-complete little operations. And these kinds of Petri nets we call high-level interface nets. So high-level because they process arbitrary data and with arbitrary operations, and interface nets because they have an interface and there's a boundary to be outside. And now let's look at a little example. So this is the Petri I've shown earlier. This is a cookie vending machine. So to understand that model, a coin goes in here in a coin slot, and then the coin ends up in the cash box, and a signal is produced on the signal place, and then a cookie box can appear in the compartment. And when all three cookie boxes are consumed and have ended up in the compartment, then this cookie vending machine stops working, and it will only it will eat your money, but it will never spend it. So it's a bad cookie vending machine, but we'll look at it anyway. And yeah, and now I'm trying to show you how this is implemented in Erlang. So I need a couple of things, a couple of information from you in order to enact this Petri net. And the first is that you have to tell me the names of all the places in the net. So we had the coin slot, the cache box, the signal, the storage, and the compartment. And you're supposed to implement a function which gives a list, and all the atoms in the list are the names of the places. And the second thing I need to know is the names of all the transitions, which were A and B. And the third thing is I need to know the preset of all the transitions that you have given me. So for A and for B, I need to know which places are in the preset. And for the transition A, it was just the coin slot, and the transition B had the signal and the storage in its preset. Let's recapitulate. This is the transition A, right? It has only the coin slot as its preset place, and the transition B has the storage and the signal. What is in the poset doesn't really matter here for now. And the next thing I need to know is what the initial marking of the net is. The initial marking just contains the 3 cookie boxes in the storage, and everything else is empty. And the next to last thing I need to know is when a transition is enabled. So the transition A is enabled when in the coin slot there exists a coin. And the transition B is enabled when on the play signal there is a signal token, and in the storage there is at least 1 cookie box. And in all other cases, no transition is enabled. And the last thing is I need to know what happens when a transition fires. And these 6 callback functions make up the structure of the Petri net. And there's a behavior, and you implement it, and then this makes up the behavior. And now I'm showing you what I try to implement with this, so to convince you that this is actually useful and not just a game, which it also is. So the first thing I try to implement is a worker pool manager. So as you may know, the pool boy worker pool manager is a very famous Erlang library. It's, I think, the most downloaded Erlang library on Hex. And this is why I thought, well, if this is so popular, then maybe it's a good use case to show that this also works. So I tried to make something that is like Poolboy, a call it graph. It's a worker pool manager, and what a worker pool manager does is essentially solving a mutual exclusion problem. So you have a bunch of workers, but they are a limited resource. And you have a bunch of clients, which want to access that limited resource. And you have to be sure that each resource is only used once at a time. And if some client wants to use a worker, but there's no workers available because they're all used by other clients, then that client has to wait until some other client releases the worker, and then the process can continue. And this is essentially the Petri model for the adapted pool boy. It's not exactly pool boy, but it's something very different, very similar. So we have, in this case, 3 tokens on the unstarted place, which means that there's supposed to be 3 workers, and they get started, and then they appear on the idle place. And this is essentially the golden path that for the client to check out a worker. So when a client wants to allocate a worker, a token appears here on the checkout place. Then a monitor gets created on the client, so that when it dies, I get a message. Then a worker gets allocated and a reply gets sent out. And what also happens when a worker gets allocated is that one worker token comes from the idle place here to the busy place, and when a worker gets checked in again, the busy worker returns to the idle place, and the process can go on. Yeah, and that is essentially the first example. You have a question?
Well, I'm just very curious. How many of the vertices in the graph there came from like pool boy source code?
Yeah, so I looked very closely at pool boy source code, but the pool boy source code is Erlang, so it essentially has no intuitive mapping to a Petri net, unfortunately. And also, for example, the data structures that pool boy works with are essentially lists. Lists have an order, right? So there's the first element and the last element. But on these places, for example, there's no order. You essentially check out a worker in the order, in some order, but not in a particular one. So there's always a little bit of an impedance, a little bit of a difference between what pool boy does and what comes out if I kind of interpret what it's supposed to do here in this case. So this is a very loose interpretation of what the pool boy should do. And some of the things that pool boy does are very meaningful and are very essential to how pool boy works. But in order to stay in this representation here, I omitted some of the features to have a beautiful representation. So there's also this kind of trade-off where drop some functionality to stay in a simple world. Does that answer the question?
Yeah, it does. Thank you. Sorry to derail you.
No worries. I want you all to talk to me. Because otherwise. So, and the reason why I actually came up with Petri nets is because I'm maintaining a distributed programming language called Cuneiform. And that's essentially the driving force. I needed a way to model a distributed system that worked underneath my distributed programming language. And I wanted to model this language as a Petri net, and that's why I needed to have a way to execute Petri nets, because I didn't want to do what I told you in the beginning, have a beautiful model, throw it away, and do something completely different. I wanted to enact the model itself. And so I'm telling you a little bit about Cuneiform. So Cuneiform is a functional programming language. It's a distributed programming language. So I'm taking advantage of the independence of subterms in functional programming languages. So when you have two terms and they're independent, you can also compute them independent in parallel. And what it also does is you can integrate all kinds of other languages. So whenever you're defining a function, you can say, okay, I want this function to be in bash, and then you call the command line tool. Or I want this function to be in R, then you use your favorite R library. So it's very integrating. That makes it open. And since the lambda calculus, which underlies functional programming, is a universal model of computation, it's also general. So it's an open and general programming language that parallelizes. This is an example for source code in Uniform. So here we have a function f, takes one parameter text, which is type is file, and outputs a record with one field y that is type is file. And I say it's in Perl, and then there comes some Perl code, I omitted that. And here I define a list of files, and it contains the files a and b, .txt, and then I just call that function for each element of the list. So, yeah, it's just to demonstrate that this exists. And so, there was a question.
When you say in Perl, do you have Perl syntax within those bracelets then?
Yeah, this is what I omitted. I'm sorry. So you're writing Perl code in there. So that's why I have these Mickey Mouse eared curly braces here. They're unique syntactical identifiers, so that you can actually write anything. It's like a string delimiter, if you will. And what happens underneath when we're trying to execute such a program in parallel, where you have all these parallel locations, is so you have three kinds of processes. The first, the green one here, is the client that holds the language interpreter. The second one, the master, is the scheduler that schedules the work, and then you have several workers. As many as you like. Here I have two. And whenever you send a cuneiform expression to the client, it will run some computation on it and will come up with some applications, some tasks to be computed, and it will send it to the scheduler. And then the scheduler will try to find workers for these tasks, and the workers will run computation on them. And once they finish, they send back the result. And the result goes back to the client. And then the client will do more work, and so all the four applications will be handled in time by both of the workers, and in the end, I return the value that constitutes the result of the computation. And this is actually straightforward, right? We have three interfaces. The first is the interface between the user and the language client, the interpreter. The second one is the interface between the client and the scheduler, the master. And the third interface is the interface between the scheduler and the workers. Wrap up, yeah. So essentially, we end up with these three Petri nets. And these three interfaces, which are represented by places in the Petri net. And I will only show you the middle one, which is the master. And the master does essentially does a lot of things. It acts as a cache, so when you ask it for some computation twice, it will only reuse the results. It acts as a scheduler, so choose the worker. It needs to be fault tolerant, so clients can die, also workers can die. It has to handle that, and it's language independent. So I'm using cuneiform, a cuneiform interpreter, but I could use anything else too. And this is essentially how this looks in a Petri form. We have here the scheduling part. Then here the structure is essentially a cache, and then workers can be added, workers can die. Clients can be added, and clients can also be added. And we're using this essentially for bioinformatics. This is a variant calling workflow where we use KADK, and there's all kinds of fancy stuff falling out. We're not going into detail here. I'm just saying, so this is not a new idea. Yeah, several other people have tried this too. Most importantly, CPN tools. which is a graphical editor for PetriNet, but it can output Erlang codes. It's also very, very close to what I'm trying to do. Then also there's a GenPM library, but it deals only with elementary PetriNets. We're dealing with high-level PetriNets. And then there's Haskell-colored PetriNets, which provides functional embeddings from a PetriNet specification in Haskell. It's also very close to what we're doing. So, really wrapping up now. We're having PetriNet as a programming model, which is super good because earlier we only had these on paper. Visual representation of code is very useful, and we can compose. I didn't actually say this explicitly. We can compose distributed systems from these, because on the inside, the process is a PetriNet as we specified it, but to the outside it's an Erlang process, and we know how to combine Erlang processes to form distributed systems. And that's it. I will thank you for your attention.
I'm going to ask Mitchell to start sitting up. Okay, but we have time for one question.
So, your code is now expressed as a PetriNet, but you also showed visualizations. Are those generated automatically in code?
No, this is Inkscape. Yeah, I did draw these. So it would be nice to have an automatic visualizer that arranges everything perfectly. But yeah, this is my handwork.
But don't you have enough information to generate some stuff?
Yeah, it's a little bit of an art to arrange these things. Like the golden path is always in one line. And stuff like that. How do you know automatically what golden path is?
Maybe you should label it.
So you need more information. That's true. Yeah.
Okay, thank you very much.